Alright, in last video we talked about the inertia frame and body frame, and we covered right-handed frame and right-handed rotation. This video we'll talk about the yaw, pitch, and roll. So essentially, yaw, pitch, and roll are Euler angles defined to essentially give us a common foundation to describe the altitude, to describe the position of your vehicle. In this case, let me give you a little bit more explanation. So let's say if this is the north, and if the plane itself is like flying in this direction, in this case the yaw angle is actually defined by your body frame. This is your IB. If you don't know the body frame, you can review the first video. And then this is your JB, which is your y-axis in body frame. And then the yaw angle is actually defined as Greek letter psi, I believe. It's pronounced as psi. And then you can see that if the yaw angle is like 30 degrees, your vehicle is like on the horizontal plane, rotates again, from the north to the right as 30 degree. As a review, this is a right hand rotation against the z-axis. Why is that? Because your z-axis is like I'll give you a question. Is the z-axis actually pointing out of the page or into the page? I'll give 1 minute. Actually, 1 minute too long, but essentially, as a review, we use right hand coordinates, where your index finger is pointing towards the x, and then your mid finger is pointing towards the j, the y, and your z-axis is actually, in this case, going into the page, right? So your z or k, kb, is going into the page. And then the right hand rotation is essentially your thumb point into the page, rotate against your z-axis or k-axis. So that's why the positive direction of the yaw angle is defined like that. That's your yaw angle. And we know we also need an angle that describe the on the vertical direction, your or vertical plane, your nose of the plane pointing up or pointing down. That is the one we use to describe that is called the pitch angle, which essentially if you look at your plane like that, and your pitch angle is like, this is your horizontal plane, and imagine initially your nose of the plane is like along with that, and then this is your body frame, your nose, which is IB, right? Actually use superscript. And then similarly, this is your JB, and then that's your Z. But it doesn't matter about JB or and Z. It is really the horizontal plane. and then the angle between your horizontal axis and your IB axis. That's essentially defined as your theta. Again, this is sort of defined as a so-called right-handed rotation. In this case, is against your the yaw is against the z axis, right? And this so-called pitch is actually it's actually against the y-axis. Why is that? Because in this case, we are essentially rotating against this JB and also the J, right? This is your horizontal axis, and then maybe from the drawing it's a little bit hard to say, but if this is your wing axis, and then what happened is that you're rotating against this y-axis up and down, right? That's essentially why we are defining like a right-handed rotation against the y here, and y is like perpendicular to that plane here. That's why pitch is like a right-handed rotation against the y. And then we also need to describe like we also need to describe in this case the raw angle of the plane, which is if it has a right wing and left wing, if it rotates in this direction, in this case is the right wing will be higher than the left. So let's draw the plane like that, like plane is flying out of the page, where this is its plane, this is plane, this is its nose, flying out of the page, and this is your vertical line, and let's say your body frame, this is your KV, where your axis pointing out of the page, where your axis your IB, and then your J will be based on the right hand rule again. It will be the left wing here, which is your JB. So this is defined as a again a right-handed rotation, right, to your like across the x-axis. And if you're pointing up, the angle is in this direction, is the right-handed rotation positive. So if we define this as vertical, we'll define essentially this angle as the say it's pronounced phi in Greek letter. So and when phi is 0, right, when phi is equals to 0, you will see that the plane is actually fly horizontal like that, right? This is like a initial position, phi is equals to 0, but when phi is positive, it will rotate like that. So this is like three angles called the yaw, and then the pitch, and as well as the so-called roll to be used to describe the rotation of our plane in different directions. And we can see these are actually rotation against a certain axis, which is actually defined as a 2D rotation. So we are using like a series of 2D rotation to represent the final 3D rotation. This is usually defined as a Euler format. So rotation in 2D about z-axis, about y-axis, and about x-axis. That's what we just talked about. And then the rotation in 3D can be described as a sequence of rotation in 2D. And this is like we use the Euler angle, yaw angle, pitch angle, as well as roll angle to define. But one thing we need to pay attention to when we use this Euler angle to describe the rotation is essentially the order matters. So if you do like rotating across z first, y first, and x first, then x, it is different than if you do x and y and z. I will explain a little bit on that shortly. So rotational matrix, before I actually show you the math behind it, I would give you like the so-called rotational matrix is defined like this. It is essentially converting ourselves from the NED northeast down frame, the inertia frame, to the body frame, and it can be defined as a multiplication of three matrices, where this first matrix is defined against the in this case the yaw angle. The yaw angle. So it's cosine, sine, psi, 0, and then negative sine, psi, cosine, psi, 0, and then 0, 0, and 1. And then the second, or the middle rotation matrix is a 2D rotation matrix that defined against the I believe this is your, let's check, the theta is like your pitch angle. And of course this is like yaw is rotating to, against z, pitch is rotating against y. So it's cosine theta 0 and negative sine theta 0, 1, 0, and sine theta 0 cosine theta. And then we have the third rotating matrix where it's rotating against x, and then it's your roll angle, and it is defined as 0, 1, 0, 0, and 0 cosine phi, sine phi, and 0 negative sine phi and cosine phi. So this is a rotational matrix where it will convert any vectors inside the inertia frame to the vector inside the base frame, actually body frame. This is just rotation. We know that when we talk about the frame, inertia frame, north, east, and down, there is also a translation. There is a center here, and the center on the body, on the plane. So there is a translation here. We'll talk about this translation later, but not right now. Let's focus on just the rotation part. When you have a body frame pointing to the nose and then down towards there as your Z, and then you have Y. So this is your body frame, this is your inertia frame, and then when we have certain vectors, we how we represent that vector in the body frame, if it is given in the inertia frame, we use this rotational matrix. Knowing that, I will show you how this is derived. The yaw angle here, if you look at this is like exactly same as when I derive equations when I do a 2D rotation in against the z-axis. And here, for general purpose, I used frame 1 and frame 0, and we have a rotation. The frame rotates against frame 1 rotates against frame 0 by theta, and similarly, in terms of the northeast down frame, right? We defined our so-called yaw angle as the angle between your body frame as well as your north, right? That angle is defined as psi in our previous page, defined as psi. So that's why that psi is essentially defined the same thing as right-handed rotation. So you can essentially unplug the theta and put the psi here. But essentially how it derived is, if we have a vector p here, and we could represent it in frame 0, we could represent it in frame 1, and then px0 is the projection on the I0 here, the I0 axis, and the py0 is of course projection on the J0. And in this specific case, pz0 is actually 0, but I wrote it anyway for general purpose. And then frame 1 is same thing. It's just the projection will be a little bit different. And then we could equal each other because they are all this p vector. And then we use a mathematical trick called dot product. And dot product has a property that we can use is, if we have two vectors, we dot product them together, it is the magnitude product multiplied by the cosine angle between the two. And when this angle is perpendicular 90 degree, this thing will be 0. So that's why when I dot product this vector represented in frame 1 with the unit direction I1 here, it will extract the magnitude of px1, because dot product of these two, they are all unity vector, and then the theta between those two are 0. So it's 1 multiplied by 1 multiplied by cosine 0, which is 1. And then px will be extracted, and then this G1 dot product I1 will be 0 because they are perpendicular to each other, and K1 the same thing will result in a 0. So that's how you wrote this part. And then using I1, right, dot product with this part, it will be equals to this one. So similarly, I could write that for the y-axis projection by dot product the vector with the G1, and similarly dot product G1 with the vector in frame 0. Similarly, we write for z, and if we consolidate it into a matrix format, this is actually the rotating matrix that can be used to, if we are giving a vector in 0 frame, we multiply by that matrix, it will give us the representation of that vector in frame 1. Okay. So interestingly, right now we are talking about the frame rotation, but if we fix the frame, we are actually rotating the P backwards by theta. These are essentially the same thing, right? If you think about, initially you had the P in frame 0, and then that has a projection like that, and then if you think about this frame as frame 1, the projection becomes that, and then we are actually rotating the P. So the rotation I'm trying to say is the rotation matrix has two uses. One is like if you think about the frame is rotating, you can compute the representation of P in the new frame if you're giving the representation of P in the old frame. On the other hand, if the frame is fixed, if you multiply by that rotation matrix, you will get a new vector that is actually, in the same frame it is rotating backwards. Just a thought. But essentially, when we have this rotating matrix, it's very easy to get the conclusion that the I1 multiplied by I0, I1 dot product I0, it is actually cosine theta, right? So that's why this first is cosine theta, and then I1 dot product G0, I1 dot product G0 is the 90-degree minus theta. So using trigonometric, you will get a sine theta. I will not go through all of them. This is just show you how this is derived, and then this matrix itself is a 2D rotation and against the z-axis, which is exactly what we did for defining the yaw angle, right? That's why the yaw angle here, is matching that. Similarly, rotating against y, a 2D rotation against y, is exactly matching this derivation here, cosine theta 0 negative sine theta. That's essentially, we have a right-handed rotation from the I0 to I1, and this is rotating against the J, so against the y-axis. We did the same thing. We rotate against the y-axis, right? And then that is, why this is matching the derivation here. So once you understand all this, the derivation becomes very easy. You always get this matrix, and then when we talking about I1 dot product I0, the I1 dot product I0 in this case, this is theta, so it's cosine theta, which you get cosine theta here. And then the I1 G0 is I1 G0 pointing, it's perpendicular to I1, so that's why you got a 0 here. And then the I1 dot product K0, right? I1 dot product the K0, you have a 90 degree plus the theta, so it's a cosine theta 90 degree, which using trigonometric property you get the negative sine theta. That's how you get this rotation matrix, and similarly you can try it out. If you have coordinates right-handed rotation about your x-axis, you will get this answer. So after knowing how it is derived and how these angles are defined, next time you only need to go through all this math. Usually you just what you need to remember is these are rotating matrix, and then we decomposed the things in 3D, right? The rotation in 3D, rotating from your so-called inertia frame to base frame. We can decompose it into 3 continuously, 3 sequence of 2D rotations against the axis, against y-axis, and against x-axis. Because the way we multiply the matrix, the first is actually the z, and then y, and then x. Changing the sequence doesn't work, right? You can prove by yourself that the sequence matters. One way to do that is you just try out, multiply this cosine phi, sine phi, negative sine phi, cosine phi, 0, 0, 0, 1. You multiply the this matrix first, cosine theta 0, and then negative sine theta 0, 1, 0, cosine sine theta 0, cosine theta. This is just not the same as this if you do the math out, right? I will do it a little bit here. Using this one multiplied by this, it will give you cosine phi, cosine theta, and this 0, this is 0. So your first component is that. However, if you multiply these two, right, your first component is actually cosine theta, cosine phi, and then this is 0, this is 0. The first one is actually the same. What about the second? The second one is like 0 sine phi 0, right? So it's sine phi. What about here? Here, your second column here multiplied by the first row, that gives you cosine theta and sine psi, right? And then 0, 0. So this is already not matching. So that essentially shows you the order matters. Don't change the orders easily. And one of the reasons that we select the pitch as the middle rotation is due to something called Gimber lock. So the Gimber lock is essentially happens when the middle rotation angle theta is plus minus 90 degree or pi over 2. When that happens, you got this so-called gimbal lock. I won't go into details. There are already tons of videos on the YouTube talking about gimbal lock. One thing that I feel useful is this gimbal lock tips tricks to avoid solve weird Euler rotations. Essentially, what happens is when the theta is equals to 90 degrees, the rotation on this plane and rotation on this one, they will fall into the same plane, so that in this case those two rotations is not is essentially doing the same thing, so you cannot move the plane in this yellow circle. You can still move however the degree of freedom of this plane is not the same as before, where you have kind of three combinations of rotation in different degree of freedom. In this case, when you have a Gimber lock, you encounter something called singularity, where essentially of rotation freedom is kind of constrained. So it's constrained mathematically by due to the way we represent the rotation by Euler angles in a certain order. So it's not really that your plane cannot move in this direction. It is meaning because the computer needs a way to understand how you want to move, and at this case, it just has mathematically U defined, and then it cannot move freely. Of course, you can kind of do some weird rotation and rotating out of the Gimber lock. Then you are having more controllability, not controllability, but having more freedom to rotate. I will not go into details about that, but that's giving you some sense why we try to avoid Gimber lock, and the way we avoid it is putting the pitch y as the middle rotation, because Gimber lock always happen when the middle theta is equals to plus minus 90 degrees, and when plus minus 90 degrees happens, you imagine that your plane is either flying straight up like a rocket, or flying like directly towards the ground. When those happens, the Gimber lock happens. So when we do the flight control, we will avoid that situation. We will never will control our plane such that we will not do that kind of movement, and that rarely happens. So that's why we define the pitch angle as our second rotation angle, the middle rotation angle, because it will never reach 90 degree. Imagine if we use others, yaw, it's usually it will becomes like a 90-degree more frequently, so that we don't want the gimbal lock to happen, and then the computer kind of stuck and don't know how to rotate. So that's a little bit side talk on why the Euler rotation is defined as the yaw first and then pitch and then the roll. Alright, I think I covered mostly all the stuff. Since this video is long, so next video I will essentially cover this table, which introduced a little bit more terminologies, like angle of attack, set sleep angle, course angle, flat path angle, and crab angle. So those are terminologies that we need to understand in order to learn the vehicle dynamic control. Thank you.